This video is about a really important topic in Octave and MATLAB regarding vectorization. So last time we learned what the word vectorized means, and so there's a very important detail about vectorization that we're going to end up with. In the meantime, there's a handful of housekeeping stuff that we're going to do. So there's a little bit of housekeeping in the beginning, and then we're going to get to this really important topic. The first housekeeping step, if you look at your desktop, is that there are two Octave icons on there. There's one that's CLI, that means command line interface, and that's just a low-level one. The one that you want to always click on is the GUI one, the one that says GUI on it. And so that's the one that kind of brings up your environment. And of course, you can see a lot of aspects of your environment. On the upper left is the workspace, where it's going to show variables and how big each variable is that you create. And then the main thing is that you're looking at the command window, right, on the right. The command window is where all the action really happens. Those are the two main spots that we talk about. There's a third spot, and that's this command history, where you can see what you've typed in the past. That can be helpful too, and so we might use that off and on throughout this lecture series. I simulated the commands that we did just up until the end of last video. And you can see this thing where we plot the sine and the cosine using this variable z. So that was kind of where we ended there. And I wanted to talk about a couple of housekeeping commands that help you clean up your space, right? The first thing is that a lot of times when you're using Octave or MATLAB and you're going back and forth between the command window and looking at figures, a lot of times you go back to the command window and the figure's in the background. It's behind your MATLAB or Octave environment, and then you type something out to sort of fix, like, if you're changing something about the this plot, or you're making a new plot, you can't find it. It's behind there. You may not be able to see it. And so sometimes it's a good idea to close up that figure each time, and then as you do the plot command again, it'll just reopen the figure, and the figure will come up on the front. So that's the command to know about, is close. So if you type out close, right, and then you can still see the file, you can still see the image, the plot in the background there when you're typing on the command window, and then press enter, you can see it goes away. So close is a way to close figures, and close space all is the way to close all the figures if you have a whole bunch of figures open. That's just a nice handy text way to close all your figures instead of going in and clicking all the corners. Good? All right, so that's one command, close. Another command that's good to know is clear. Clear gets all the variables out of your workspace, so you can start from scratch again. It's like starting with a new, with Octave just coming up from scratch. And so clear is another good command that eliminates all the variables. So if you type clear, you can see the variables. As soon as you press enter, all the variables in the workspace goes away. So those are two good commands. The third command is CLC. So I have all these commands, you can see all this stuff. So CLC just clears the command window, so it gets to the top, so it's nice and pretty. So some people like to do that too. So close, clear, CLC. Those are commands to kind of start afresh, start from scratch, kind of. That's I like doing that a lot. And so those are just three commands I thought I'd teach you at the beginning of this lecture. Okay. In order to teach you about this new trick with vectorization, I'm going to calculate the tangent, basically, is what I'm going to do. So I start with the same time array. T goes from 0 by pi over 8 to 2 pi, that's 17 elements. Now, I did it all in one line here, if you notice. I put it in parentheses and then put the prime in there, so it's a column from the very start. It's not rows, right? That's kind of nice. So you can do that all in one step. And then I said y equals sine t. Now notice one thing here is that I put a semicolon after y equals sine t. What the semicolon does in Octave and also MATLAB is it does the command you want. If you look over in the workspace, y is there. It's a 17 by 1 array, just like time is. It's the same size as t, right? But it didn't show up on the screen. It just suppresses that echoing output. most commands you're going to do is you're going to suppress that. You don't want to see all this stuff, especially if you're doing with hundreds and hundreds of data points. You don't want to see it all the time. You just press semicolon, and it doesn't show up. Same with z. Z equals cosine t, semicolon, doesn't show up, but z, nonetheless, z exists, and you can see it in the workspace. So that's what semicolon does in Octave and MATLAB. Now, what's the tangent? Well, tangent is just sine divided by cosine. There's a tangent function in MATLAB. It's called TAN. I'm not going to do that. I'm not going to call it that. I'm going to call the variable that I'm going to calculate TNG, so that it's different from the actual function tangent. So I say TNG is equal to y divided by z. That should be easy. It's vectorized after all. It should work. What? Well, it didn't work because I look over there in the workspace and it's 17 by 17. It's not 17 by 1. The tangent should be the same size as sine and cosine, right? It's just 1 point for each time point. It didn't work. It's 17 by 17. If I do TNG equals y divided by z without the semicolon, it just spits out all the stuff and you can see a bunch of numbers and none of them make sense and I don't know what's going on. It's weird. What is that? Well, it turns out that because MATLAB and Octave are built for matrix functions, a lot of simple mathematical functions are overloaded, meaning they mean more than just what they are. So the forward slash means if you're dividing by 5, right, and we've divided pi divided by 8, so I know that it's the normal division symbol. But when you do one vector divided by another vector, it might be vector division, or like the opposite of vector multiplication. And that's exactly what happened. If you divide a 17 by 1 by another 17 by 1, you're going to get a 17 by 17. If, for example, I do y prime divided by z prime, so TNG equals y prime divided by z prime, you get a single number. So a 1 by 17 divided by a 1 by 17 is 1, right? So slash means some kind of matrix manipulation, some kind of matrix calculation, matrix division, really. Wow. Okay. And if you notice, I made a little mistake there. I didn't put one of the primes in there. If it can't be done, right, it'll just give you an error. So all the permutations of prime and not prime are not going to give you a 17 by 1. It's not going to give you the right answer. We have to find there's something wrong. We're not doing the calculation right with the division symbol. This leads to an important topic. We want to do row by row division. That is, we want TNG1, the first element of the TNG array, to be equal to y, the first element of the y array, divided by the first element of the z array. So if you think of it in terms of an Excel spreadsheet, you have a y column and a z column, and you want tangent, you want c sub 1 to be equal to a sub 1 divided by b sub 1, and c sub 2 to be a sub 2 divided by b sub 2, and so on. Right? So if you're looking, we want to do row by row division. In MATLAB, that's dot. You have to use a dot there. So dot divide is row by row division, and dot times is row by row multiplication. So if you say that TNG is equal to y dot divide z, then now that looks like it's an answer at least. Let's plot it. So we plot t comma TNG. Does that look right? I don't know what that looks like. That doesn't look like the tangent to me. Oh, I see. Look at the y-axis. It goes from plus 10 to the 16th, 5 times 10 to the 16th, to minus 2 times to the 16th. It's really, really big numbers. Because tangent goes off to infinity and minus infinity, you were just doing, it's a numerical technique, we're just looking at really, really big numbers. We can't really see it. So we have to rescale the plot. And the way to do that is with the axis command. So you you just type out the word axis, then open parentheses. So in the function name, the function of the argument list is going to be parentheses, and then you give it an actual array. It's going to be 4 elements, and it's going to be in square braces. So it's going to be x min, y min, x max, y min, y max. So I want to go from 0 to 7. That's greater than 2 pi. That includes 2 pi in it. So in the square braces, I put 0 space 7 space, and then from minus 2 to plus 2. So minus 2 space plus 2. So when I type that in, then I go back and look at the figure. All of a sudden, yes, and lo and behold, that does look like an actual tangent function. So that it looks okay. You can with GUI stuff, you can actually change the axes, but axis is such an easy command to know. It's probably easy to do by text, so that's why I always do use the axis command. Just for completeness sake, let's look at the actual real tangent function. So if I just say plot t comma tan of t, I get the same looking plot. And then if I do the same axis, right, 0, 7, minus 2 to plus 2, I get the same plot as I did when I manually calculated the tangent. So dot divide and dot times are row by row multiplication and division and multiplication respectively. That's the lesson to learn, is the vectorized way to do row by row calculations is by using the dot before you use the symbol division or multiplication.